Hiya folks, the old fossil here.
This video is about calibrating diode temperature sensors. I'm trying to build a little network throughout the house to collect all sorts of environmental data of temperatures, humidities, uh, status, windows closed, doors closed, that sort of thing. And I'm using only 10-cent diode temperature sensors, 1M4148, very cheap, but they work. It only takes one little op-amp section to match the diode itself to an Arduino clone. I use Adafruit Metro Minis. They have built-in A to D converters, a couple of them. There is some math in this little presentation, but don't get excited, it's just first year algebra. Temperature accuracy is hard to pin down. If you, most of the explanations you read of it say, start off by getting yourself a National Bureau of Standards calibrated reference thermometer. And of Amazon, they start about $200 a piece. So that seems to be a little exorbitant. What we're going to do here is finally wind up matching 4 individual little diodes with each other and with the refrigerator thermometer I have to within about a degree, and that seems to be enough for practical purposes. This is a schematic of the breadboard. The 4 little diodes on the left go to an op-amp compensation stage, which goes to an analog switch, so you get all 4 of the op-amp outputs into one line to the A to D converter input. The 4 diode arrangement between the switch and the Metro Mini is to limit the op-amp volts in case they get frisky and don't exceed the range of the Metro Mini A to D converter. All 4 plus inputs of the op-amps are connected to a pot so that you can adjust the bias offset voltage. This is a picture of the breadboard laid out just like the schematic. The 4 diode temperature sensors are encased in epoxy in the little plastic straw sections, which are rubber banded onto the back of the refrigerator thermometer. This is the entire operation and stuck into the freezer with the refrigerator thermometer and the diodes at the bottom and the board up on the top shelf. Okay, get ready, here comes the math. It's mostly charts and graphs and tables, a little bit of algebra, no calculus. Don't panic, don't give up, let's just push ahead. So this is what the breadboard does when it's at room temperature, and then I stuck it in the refrigerator at 47 degrees and then in the freezer at 22, and finally back out in the garage with no air conditioner. It was 88. That's what the refrigerator thermometer read. So at the 4 stabilized temperatures, you plot to get this kind of a plot. If you notice at a given A to D step, the red box says you can have 7 degrees Fahrenheit different diode temperatures to produce it. On the other hand, at a given temperature, the A to D readings can be 30 steps different. The 2 black boxes note that the board and the sensors don't have to be in the same place. If the board and the sensors are both in the temperature, you get those points, but if it's like an indoor-outdoor thermometer where it's only the sensor would be in the cold temperature, you get the other 2 points. So if you draw a line between the endpoints of any one of these graphs, the orange line, temperature sensor 1, the equation for that line is the top line in the green box for any point in between the endpoints. And your first year algebra should let you solve that function for the temperature in the second line in the green box. Now all we have to do is find the 4 constants A, B, C, D. So this is what we get. The top table is the numbers from the measured raw data, and the bottom table is the actual calibration coefficients that we're going to need. For instance, in the orange temperature 1, the A value is 325, which is the difference between the high temperature reading 461 and the low temperature reading 136, and so forth for all the rest of them. So if we apply that correction to the raw data points from the previous graph, this is what we get for the corrected readings, which is much better, as you can see. Finally, when I was first designing this thing, I kind of assumed that it was going to go from 0 to 212 because the only real temperature reference I could get was going to be boiling water. But really, that's an extended range. In actual fact, we're never going to get anything anywhere near that hot. So if we expect maybe 140 degrees for the top measurement, we could make the op-amp gain about 30 instead of 17, and just adjust the offset voltage a little bit to center it better so that the A to D converter runs over a wider dynamic range. Okay, here's a look at what the spreadsheet does. This is the current log file, which I just took. It's been running about 31 hours. Separate serial, replaces that with whatever the log file is now. This is the reference file that we started with. And then calibrate applies to correction and gets the corrected temperature readings. Excel spreadsheets use Visual Basic for the macro language. This is what the subroutine subserial does. It's the format of the dump is a long string of integers, and the next section kind of manipulates the active cell to clear the range of the data from yesterday. Next page just opens the log file and then separates the long serial string of variables into separate columns and then lists them on the spreadsheet. Page 5, the actual calibrate routine just goes onto the spreadsheet table and gets the calibration coefficients and then applies the correction formula, which is just a one line of code. Starting on page 7, just for completeness, here are the changes to the Metro Mini code to put in the analog multiplexer. You have to declare the 4 pins and change the measure routine to make the right signals high in succession. And finally on page 9, that leaves the other analog inputs in the Metro Mini available for whatever other readings you might want to take. Well, that's about it. This was a fun little project. It seems to work pretty well. It's out there now in the greenhouse, recording away, temperatures every hour. Thanks for watching.